The time has come for our second keynote, and our keynote speaker will be Mateusz Modrzejewski, who is doing a lot with music and machine learning, data science, etc. And it's very impressive. And Mateusz will talk about music information retrieval with Python. So give a warm welcome to Mateusz.
Oh, whoa. That was unexpected. Alrighty, let's do it. Hello, PyCon. I'm super excited to be here. I'm super thankful for the organizers for having me. And the topic of today's talk will indeed be music information retrieval in Python. So, hi, I'm Mateusz. I'm an assistant professor at the Warsaw University of Technology, which is this lovely building over there. I just recently finished my PhD over there, and I work at the Institute of Computer Science. I also have worked for some super cool companies, the most recent being Apple. But besides all of that, I'm also a musician. I play drums. I've played drums professionally for about 10 years now, and I've been very fortunate to play with some really cool artists and visit some places that I think that otherwise I would not have visited. So I've played experimental jazz, and we've had the opportunity to play some tours in Asia. I've played with Grubson, who is a native of Rybnik, which is kind of close from here. I'm also the permanent drummer for the band The Dumplings. And I also play children's music with Majka Jeżowska, and when children grow up, they start going to festivals, and this is how we landed at probably the craziest thing I've ever done, which was Woodstock 2019. Yeah, that was kind of a big thing. But this brings us to the topic of today's talk, which is MIR. And MIR stands for Music Information Retrieval, which is kind of an umbrella term for music, AI mixed with computer science and software engineering and a bunch of digital signal processing, musicology, statistics, psychoacoustics. It's basically a whole kitchen sink of things. So the main idea of music information retrieval is processing music in useful ways, right? Hence the word retrieval. But it has come to be in a way that this term also encompasses some generative AIs, because, you know, AIs are kind of known for their impressive generative abilities, so why not try to do that with music? But something that I am also particularly interested in is enhancing our perception of music. How do we listen to music, how music affects us, and how do we affect music, right? So these are the three main interests of music information retrieval as I see them. But before we talk about information and retrieval and AI and stuff, let's talk about music for a brief second. Who here plays any instrument, whether it be like a hobby thing or you've played sometime in the past? Raise your hand. Okay, a bunch of people. Who's confident in their musical skills? Like, yeah, I've played a couple of gigs or something. Yeah, also a bunch of people. Who does some mixing or production or processing? Maybe you have like Ableton or GarageBand and you do some, yeah, also. And who has never ever played anything like experienced music only from a listener's perspective? Okay, also a bunch of people. Okay, so I will try to find something interesting for all of the groups, but I think that we can agree that music is like multi-dimensional and complex and complicated. When we think about music, we often think about the genre, right? So I remember times where you had to belong to a group, and if you listened to metal, you could only listen to metal, you couldn't listen to anything else, right? And now there's like such a variety of genres that many lines have become blurred in this space. Music also has a defined mood, so there can be perceived mood, like this music sounds angry, or induced mood, like this music makes me angry. There's instrumentation, right? There's a ton of different instruments. Some of them are genre specific, some of them are typical for some cultures or countries, etc. There's timbre, meaning the sonic qualities of the music, how it sounds, how it's produced, what's the sound characteristic of a particular instrument or a particular track. There's also musical structure, right? Because music is structured. It's a type of a language, right? Events happen in sequences and, at least hopefully, like have some meaning transferred along that sequence. Also, going a bit deeper into music theory, there's a bunch of rules that make music sound good or bad, or make it sound dissonant and unsettling, or make it sound very consonant and very harmonic and pleasing, right? There's also the rhythmic structure of music, which can be very different depending like on probably most of the other bullet points over here. I mean, we could go on with this, but I think that we can all agree on the fact that music is a deep and complex form of expression and communication. So how do we approach such a complicated and multi-dimensional thing with computational methods? Well, let's start with just simply interacting with music, because over the years there has grown like this huge ecosystem of smaller or bigger libraries that make interacting with music using Python really simple. So let's look at some examples. Who knows what this is? Yeah? Yeah, it's a pedal board. It's something that a guitar player would use. He or she would operate it with the foot. You set the knobs to some values, and you can change the sound of your guitar without taking your hands off of the guitar, right? And pedalboard is the name of a library by Spotify. It's a library used for audio effects. It emulates some of the most popular musical effects, like reverb, which is what we can hear right now because we are in a big room, right? You can do delay, which is more of an echo thing. You can do distortion, which makes the guitar sound really like dirty and crunchy. This is used mostly for data augmentation in more of an AI setting, but you can easily use this to process any audio that you like. Perhaps you're recording something for a presentation or something like that. You would just like to give your voice like this special twist, make it sound a little bit better. You can do that programmatically using Python. It's a super simple library to use. The first 2 lines are just simple imports. Then lines 5 to 7, we read in a audio file. Then in line 10, we define just a simple list of the effects that we want to apply. We apply them in line 13, and we save the result, and that's basically it. You can create your own Python pedal board with just a few lines of code. Another cool thing is this library called Pio, which is basically like an audio synthesis engine that kind of allows you to do like really low-level digital signal processing operations. And this thing is actually used in live performances. So there's this guy named Mathieu Amiguet. I'm not even gonna try to pronounce the name of his band, but they are playing this Renaissance, Baroque kind of traditional old music with old genuine instruments. However, on stage, what they are using is a laptop connected to all of the microphones, and on that laptop, during the whole show, they are running a Python script that implements effects control, that implements looping, so the guy is able to record a short phrase of himself and play over that loop, which is awesome. And it also implements control scripts for the whole show. So basically, like the whole show is scripted within a Python script. They change tunes, they change effects programmatically, which is, I think, pretty wild. Some other cool tools that you can just take off of GitHub and start experimenting with right off the bat are augmentations, which is also kind of a data augmentation thing for deep learning, but it works very similar to Paddleboard. There's this library called PyDub, which allows for very simple audio manipulation like cropping, trimming, cutting up into segments, etc. Also, there's this library called Soundfile, which is able to read and write audio in many formats and change between that. And the list goes on, and we could find more examples of super practical libraries, but let's look at a bit of a different thing. There are also very interesting musical APIs. Two of the most famous being the Spotify API and the Deezer API. So if you're looking for a nice data source for your next application or your next personal project, why not give these two a try? Stuff that you can find in those varies from features like mood, danceability, energy, acousticness, whatever that is, musical structure like segments, beats, choruses, verses, etc., artist and song metadata, and there's also a glimpse into the recommendation API on both of those services. And many super interesting apps have already been built using these APIs. Like one example that I've got handy over here is this page called Every Noise at Once that you may know about. This is like a scatter plot of all the musical genres that are recognized in Spotify. There's like a couple of thousand of those. And if I can remember correctly, the ones on the top are the most mechanical. I'm not sure if you can see this, but on the very top it says Latin Tech House, and then it goes to Italian Tech House, then there's some dark techno, then there's like this huge cluster of musical genres that goes all the way down to Polish classical piano. So, yeah, I think this is pretty neat. You can check out the API pages to get more ideas like this. But if we're looking at data, why not look at data sets? So there's a growing collection of musical data sets. Most of them you can find on the webpage of ISMIR. ISMIR is the International Society for Music Information Retrieval, which is the biggest MIR conference which has been taking place for quite long now. There's a big list of data sets that you can use. Some of them contain audio, some of them contain features, some of them contain lyrics, some of them contain original music. It's definitely worth looking at those. And there's also a Python library that makes working with MIR datasets much easier. It's called MIR Data, and it provides wrapper and utility functions for a lot of those datasets, including the fact that you can download most of those with a single line of code. So that's pretty cool, I think. There's also Librosa, which is like the audio processing library. It offers functionalities of visualization, feature extraction, processing, getting different types of musical representations, etc. Let's say we want to do harmonic percussive separation, which is taking a recording and like extracting the percussive part of it and the whole rest. That's a single line of code in Librosa, that's line 5. And lines 8 and 9 are all that's needed to compute what's called a short-time Fourier transform and then extract a spectrogram, which is a visualization of music, and it's basically a heat map of frequencies over time. Now, visualizing music and using images inevitably brings us to machine learning and deep learning. But before that, this is not the only representation that's useful. So far, we've been talking only about audio examples, but there's also this thing called symbolic music. So this is audio, but there's also music in symbolic formats. So the most popular one is MIDI. This was invented, if I'm not mistaken, in the early 80s. And it's a binary protocol for communication between synthesizers, but you can also write music in this format. You can't listen to that music, but it's only like a digital version of the score. So you have full information about what instrument was played when, how long was the duration of the notes, etc., etc. But in order to actually listen to that, you have to put it through some sort of synthesizer system or something like that. So think about this as a kind of a digital version of sheet music. And of course, Python has a ton of utilities for working with MIDI data. So there's Pretty MIDI, which is like the MIDI processing library. There's MusePy, which is useful for MIDI analysis and also extracting metrics for systems that perhaps generate MIDI music. There's also Partitura, which does something similar. There are also other libraries like Mido and Music21, all of them created in Python and used across MIR research. Okay, so now we know how to, at least in a basic sense, process music, but let's take a look, what can we learn from music? So let's unleash the AI. So the most classic MIR task is music tagging, right? So we have audio, we put it through some sort of model, and we expect a tag as the output. In this case, this is just the genre, but modern tagging systems usually output multiple tags because classifying only the top-level genre is a little bit below our expectations. So this is something that I can't recommend enough. This is from last year. It's called Music Classification Beyond Supervised Learning Towards Real-World Applications. I think that this is a fantastic introduction to deep learning and classification in general. It contains tons of code examples and very simple explanations for the whole problem setting, so highly recommended. Also, all of the state-of-the-art tagging models have open source implementations, and you can download the pre-trained models. This is also from last year. The repository is called literally state-of-the-art music tagging models. You can download the pre-trained models and you can look through the code. It's fantastic. Another MIR task is source separation, which means that, again, we are inputting some audio to our model, but this time we want the model to kind of unmix the song, right? And this is a non-trivial task. I mean, this is kind of like trying to pick out the vegetables from a soup that's already been blended, right? That's like a hard thing. When you're mixing music, you're basically summing up all the samples, and there's no way to tell in what way where they summed. But again, turns out that neural networks do this thing pretty well. So there's this huge model developed at Facebook some time ago. It's called DMUX. It looks like on this picture. It's super terrifying, and we're not going to go into that. This architecture is what's called a UNet, and that's because supposedly it has the shape of the letter U. I'm not so super sure about that, but that's why that's how they call it. And it's basically also like an decoder-encoder structure, which you may have heard about already, even during this conference. Again, this is open source. You can download it. You can read the documentation for 3 minutes and run your audio through the provided scripts. Also, there's another model called Splitter. It was developed by Deezer. This is also an open source library. Again, in a couple of lines of code, 2 lines are the imports, 3 lines are 4 lines. Are reading the file and performing source separation with this model is like a single line of code. You can also start experimenting with this right away. And this thing is actually deployed in some music production software. There's this VST plugin VST plugin company called Isotope, and they use this in a plugin that allows you to unmix the song that you're working on, in case like maybe you received a mixed track from somebody who didn't do their job really well. Now the song isn't mixed until you say it's mixed. There's also a library called Nozzle. It was developed by Ethan Manilow and a bunch of his friends from the Northwestern University. Apart from deep learning models, it also contains some more traditional approaches like non-negative matrix factorization and a bunch of others. And the library also includes a Gradio interface. So you can just run this in the browser and also start experimenting with this right away. Okay, so this was source separation. Now let's go into transcription. So again, our familiar problem setting, we've got audio, we run it through some kind of model, but this time our output is symbolic music, right? So we're basically training a model to learn to transcribe what it's hearing into a different representation, like basically as if it was writing it down on a piece of paper. Here, I think that the most interesting thing that you could look at right now is a model called Basic Pitch. This is also by Spotify. This was released, I think, like 3 months ago or something like that. It has a web demo. You can read through the code. It's all on GitHub, and it works fantastically well. I've tried it both on multi-track recordings, which is the use case that they claim they don't support, and it still was able to pick up the notes with like really high accuracy. Very interesting thing as well. Music recommendations, like that's a whole topic of its own, right? It's a immensely complex topic with massive business and cultural impact, as recommender systems are in general. It composes out of a bunch of different subtasks like tagging, like information retrieval, like ranking. There's a lot of engineering, especially if you're working with really big data. You have to have the room for A/B testing or performing other sorts of tests. But music recommender systems are what actually kind of drives how we listen to music nowadays. And of course, once again, there's a whole Python ecosystem for developing recommender systems, not only music recommender systems, but recommender systems in general. And some of the ones that I would encourage you to look into are Spotlight, Surprise, Implicit, Light FM, Pandas, because if your recommender system can be written in a single line of Pandas, then that's fantastic. That's awesome. You've just saved yourself a lot of problems. And also you've got support for neural recommendations in TensorFlow and the latest version of PyTorch as well, I think. Music representations. We've already talked about audio. We've already talked about some symbolic representations. Well, is there something in between? Turns out there is. You've probably stumbled upon the term embeddings when talking about deep learning and machine learning at least a couple of times. So what's an embedding? An embedding is basically it's a vector of numbers that's meaningless to a human, but hopefully it encapsulates the data in a way that's very meaningful to ML algorithms, right? So again, there's this model called OpenL3. It's trained in a very interesting way because it's basically two neural networks in a audio-video correspondence tasks. So we feed 1 second of audio and a single frame of video into the network, and the network's task is to say whether those two pieces come from the same recording, whether the audio corresponds with the video. And what this network does while trying to learn this task, it learns to produce these embeddings, like these internal representations, which are just vectors of numbers, both for the music part and both for the video part. And then you can just use one part of the model to embed your audio and then perform any downstream task that you like. And this particular model has already been shown to outperform some of the other representations quite a lot. Okay, and there's a ton of other tasks like beat tracking, pitch tracking, chord detection, tempo estimation, structure analysis, artist similarity, specific musical domain clustering, and music training tools. There's a bunch of companies that are interested into research like this. Yamaha is doing some very interesting research in tools that help you to learn to play an instrument. There's also great stuff coming out of Dolby, Adobe, Pandora, and some of the other companies, TikTok, ByteDance as well. Okay, but let's get to the part where we get to listen to some stuff, which is generating music. There's two ways that we can generate music. I mean, there's many ways, but there are two ways that we use neural networks for. One is neural audio synthesis, and the second one is symbolic music generation, or like AI composition, we may say. So again, in the first case, we are generating audio, so something that we can listen to. In the second case, we are generating only the symbolic music, which is like the composition that you then have to manually as a human, or perhaps using some different tools, turn into audio, right? This is like if you had a piece of paper with music and you're giving that to a musician to perform. Okay, so let's start with neural audio synthesis. The use case for this came actually out of speech synthesis, because right now we're pretty accustomed to having assistants on our phones. You can say the magic word and ask your phone for directions, and it speaks in a pleasant human voice that's synthesized. That's not really recorded. So the big breakthrough came with PixelRNN and WaveNet. This was developed by Aaron Vandenoort. At Google and DeepMind in 2016, but since then we also had DDSP from Google Magenta. This is another complicated chart, but the main takeaway is that this basically works like a synthesizer. So you've got the knobs that control how the output sounds like. You have a volume knob that makes the signal louder or quieter, and you've got a separate input for the pitch, which are the keys. And what this enables, let me just show you. This enables stuff like tone transfer.
Tone transfer is a technology developed by the Magenta team in Google AI. It allows you to deconstruct sound into Play-Doh and enables you to mold it into something else. So if you took the sound of birds chirping, or if the sound of you singing, ooh, ooh, it can remold that input into the sound of the violin. We do this by training a machine learning model to distill what makes an instrument sound like that particular instrument.
Whatever would that sound like? That's beautiful.
Yeah, that's what I think too. I mean, flute is kind of difficult, and like all of the woodwinds and the reeds and the brass instruments are really difficult to synthesize because you use your lungs and you use your face to mold the sound. So this is like a really cool thing that's enabled by this model. It's basically a bunch of DDSPs trained specifically for particular instruments. Then there's also OpenAI, of course, who proposed this model that's called Jukebox. So Jukebox is a neural net that generates music, including singing, as raw audio, and it's basically able to imitate and produce previously unheard music given a prompt. So let's see how that works. So I really like that the OpenAI Jukebox article says 12-minute read and 10-day listen. We don't have 10 days, so let's just listen to one single example, which is Scary Good, and this is music in the style of Elvis Presley.
Dusty, tiny, almost scarred, but the little hitch tells the heart. When my toe slips, when my hair was sizzling fine. At last, when he woke up with a mind. I'm Dusty, King, this friendly help from Goethe to the picture rack. When he sees he was victorious, listen, please.
Okay, so this is not an actual Elvis Presley song. This is something that was totally hallucinated by the neural network. I mean, you still can hear some subtle artifacts, like the audio, like it seems to kind of drop out at some points, or like seems to get filtered, but music from those times had different sound quality than we have nowadays, and also these systems aren't like super perfect. This isn't like DALL-E 2 levels of, but we're getting there. Okay, So this is Jukebox from OpenAI. Now, then, has anyone heard of the band Databots? This is probably my favorite example out of all of these. So Databots is like a duo of programmers slash musicians. Their motto is eliminating humans from music. And they create neural networks that are able to imitate any band that you want. They use a variety of models. Also, they rely on Jukebox for some of the stuff. But basically, one of I think their most outrageous and ridiculously awesome achievements is this live stream called Relentless Doppelganger, which has been playing non-stop and live streaming non-stop for over 3 years now. And this is like a live stream of technical death metal hallucinated by a neural network. It's absolutely outrageous. Let's listen to a few minutes of it. A few seconds maybe, maybe not minutes. I mean, first of all, death metal is like a specific type of music. I've listened to this for quite a long time. If you kick in at just the right moment, you just get a stream of something that actually does sound like technical death metal. And this is live streaming since 3 years, so just tune in anytime you want to hear some neural network generated death metal. But Databots don't stop there. They have this song called Nuns in a Mosh Pit that's even more ridiculous. There's like 7 or 8 different models in this song. And this is a note from Databots. We generated nuns singing Hail Satan, Death Reese, breakbeats, Guitar Pro riffs, and more using sample RNN, Jukebox, catch-a waveform, qubit neural synthesis, conceptual synthesis, DataGP, and raw audio diffusion. Then assembled the pieces together in Ableton. So let's listen to just a few seconds of Nuns in a Mosh Pit because I think it's absolutely amazing. It sounds like a child of Aphex Twin, the band Behemoth, and Jeffrey Hinton. So these are the Nuns. Okay, let me move a bit further down to the Jukebox and to the stable diffusion part. And now stable diffusion kicks in. I mean, it's just totally outrageous, right? This is what happens when you have too many GPUs. Okay, and there's also symbolic music generation, because these examples were mostly of, I mean, they were all of raw audio generation, which in all cases is much more difficult than working with and generating symbolic music. For symbolic music, I think that the most applicable and maybe like good sounding in the traditional sense models come from Google Magenta, which is like a subdivision of Google that specializes in MIR and computational creativity and that sort of stuff. So they proposed a bunch of models during the past few years, including a music transformer, a variational autoencoder, recurrent neural networks, and also many of their ideas are already published as VST plugins, which you can just download, import into Ableton or any other software that you're using, and just start playing with neural networks for making music. So let's take a quick look at some of the models. So this is Music VAE. This is an example of interpolating between two MIDI samples. This is the first one. The second one. Interpolates between the first one and the second one. Yeah, so you could hear how it went from the first example, started incorporating some of the faster notes from the second example, etc., etc. This is because of how variational autoencoders work. There's even been a talk about these models today. So if you like this, I encourage you to read more about autoencoders and about variational autoencoders, because these are pretty powerful models, although this is not the newest architecture, but they are pretty easy to train and work very well for a variety of tasks. However, this is an older model. This is just a recurrent neural network hallucinating some music. And I think this paragraph sums up this example pretty well. I mean, locally, this makes a lot of sense. It sounds like an actual piano performance. But what we are lacking with just plain recurrent neural networks or LSTM models is the capability to model some longer dependencies. And as probably some of you know, we already have a solution for modeling longer dependencies. This is something that was originally used for natural language processing, which is the super powerful neural network architecture that's known as the transformer. It basically borrows a couple of ideas like attention and self-attention from computer vision. So let's compare how that sounded to a music transformer, which is much better in making like long phrases that still make sense. I mean, that's pretty cool, right? That like actually sounded like part of a piece. I mean, the rhythmic pattern was very consistent. It sounded like one whole musical idea, and the capabilities of networks like this go far beyond 30 seconds. Alrighty. Yeah, some of the other approaches include generative adversarial networks, which is also another type of neural network where you actually train two neural networks. And one is trying to generate fake data, and the second one is trying to determine the fake data from the real ones. This has also been applied to music. This is called MuseGAN by Hao and Dong. And the interesting part over here is that, again, it's MIDI, it's symbolic music, but they are generating multiple instruments at a time. So it's not only like one piano part, but you can generate like a whole band with this, and there's even some consistency between the harmony of one instrument and the second instrument, and the rhythmic patterns of one instrument and the second instrument. So this is pretty interesting as well. Also, older models like plain recurrent neural networks in the LSTM or the GRU or the other flavors work reasonably well as well. And also even the classic solutions like a Markov model, which is like a probabilistic model, right? You just basically have a matrix of probabilities. Like this note is this probable to occur after this note. You put your training MIDI through a Markov model. It just basically learns to estimate the probabilities for a note happening after another note has happened. This is fairly simple. You can implement this in a couple of lines of Python. And here's an example of a plain Markov model. I mean, here are two Markov models. One is for the pitch, so for the particular note that is played, and the second one is for the rhythm, so for the duration. And here's a Markov model hallucinating snarky puppy solos. I mean, this sounds totally like a decent jazz fusion solo, but the case here is that Markov models kind of repeat what they already heard. So we could also have a chat about how that goes with creativity and novel composition, etc. But that's a whole different topic. Okay. So one thing that I would also like to kind of pinpoint is like the cultural impact of MIR, because the recent years have seen a growth of interest in like the cultural impact of how we're using AI in music. And what's clearly visible in this research space right now is like looking for more diversity and discovery, and including not only Western music into this type of research. There's emerging topics of like Indian music or I don't know, East Asian music or South American music, which is super interesting, and I think that those are extremely valuable and interesting topics that totally should be included. We know already from NLP that if you wanted to do some language modeling that wasn't in English, it got kind of harder. So it's really great to see that also in the music space, there seems to be this kind of a reach out for diversity and discovery. And okay, I think it's slowly time to sum up. So I think that at least I've tried to convince you that MIR enables new experiences both for the listeners and the creators. Autonomous music AI is still kinda immature, so I don't think we have to worry about AIs taking over musicians' jobs like anywhere too soon. But it already enhances human creativity in novel ways. Besides, the development and the progress in music has always been in kind of a tight feedback loop with the development and with the progress of technology. So I think that this is just a natural next step in that evolution. And I hope that I was able to successfully convince you and give you a glimpse of the fact that Python already has a super rich ecosystem for interacting with music. That's it. You can find me all over the internet using this handle. My name in the internet is @Modrzejewski, and I'm very happy to have had the occasion to talk to you today. So thank you.
So now we will move to the Q&A section. So the first question regarding source separation. When ML model is trained, how it is recognized that sources were correctly separated?
Fantastic question. You may have seen in the slide that I showed that the source is separated into 4 tracks: vocals, bass, drums, and other. And this is the most common setting for source separation, because like the first big data set that was used by almost everybody had this type of separation. So in the data set you had the mixed track and like the separate tracks for those 4 parts. So vocals, bass, drums, and all the other stuff. And this is kind of how the source separation setting has grown over time, although I think that it's expanding a bit right now.
Okay, next question. Is there a way to retrieve information about used vocal effects through some model?
About the effects, I'm not sure if I've seen some research done into like reverse engineering the particular effects, like how much echo is there on the vocals and how much reverb there is, etc. But I think that probably just I haven't heard about it and somebody's doing it already, and if not, I think that this is also a great idea. But haven't heard of any like solutions that like have made it to the headlines.
Are you scared that AI will eventually be better than people and we will end up with geeks without musicians?
Oh yeah, this opens up a whole separate can of worms. I don't think so, but this is I think that there's still going to be, you know, like this human factor in live performances. I mean, we like to watch other humans do difficult things, like run really fast and swim fast and climb mountains and stuff. And there's a certain enjoyment of like watching people play, you know, live music that I think that isn't going anywhere. Yeah, I'm mostly for like human and machine co-creation. Although, like looking at data bots, there are people who are already trying, you know, to make that vision happen. So I guess we just have to wait and see what happens.
Okay, next question. Are there tools that manipulate or analyze mod files too?
What's a mod file?
Mod file was used on Amiga and Atari, I believe, and you could have different, I don't know how to call it, instruments or samples, and you could, in a way, it's similar to MIDI, that you have notes and some instruments or samples.
Yeah, like in cases like these, like my answer, I think always will be like probably someone has already tried this because like MIDI isn't the only symbolic music format. There's also something called ABC. There's Music XML. And a couple of other ones, but those are much less used. So if I had to guess, I'd say that, yeah, probably somebody's implemented like some library for using mod files as well.
Okay, next question. Ableton or FL Studio?
Ableton. This is a simple one.
Next question. Do you think Python is fast enough to be suitable for live synthesis with acceptable latency?
I think, yeah. I think it is. Some of these synthesis models are already super fast. Some of those, like, I don't know, like, let's say jukebox, where you're synthesizing like a whole song, that does take a long time. It takes a long time to train, and inference time is also pretty long. So you need to have that time look ahead. But some of the smaller models, I mean, you could definitely use it. Use those in real time when the models start having enough controls to do that. Also, right now there's quite a bit of research in making the neural networks, the models smaller. Like for instance, using pruning where you're searching for like a smaller subnetwork within a bigger neural network, and you're expecting the smaller network to do the job just as well as the bigger one. So I'd say yeah, it is. And the non-deep learning stuff, that's definitely already suitable for live performances.
Did Mir boost your creativity in creating your own music? For example, did you create a tune based on a Mir output?
Yeah, I did, and it was a very inspiring process with Michał Milczarek. That's the guy that we have the jazz trio with. We released this like experimental, obscure mini AP album with like 8 songs that were generated. The MIDI was generated by a generative adversarial network that we trained, and Michał just processed those. Like he chose the synthesizers, he chose the effects, the processing, mixing, etc., etc. So like the network produced the samples, but then they were heavily post-processed and synthesized by humans. The EP is called Drop, and you can listen to it at SoundCloud or Bandcamp. Maybe I'll post a link in the Discord later, but it's still somewhere in the internet.
Okay, next one. Can we tell that AI is being creative?
Oh yeah, creative and sentient. This is a hard topic. I mean, evaluation of generative musical AIs is like a sub-problem of its own, because how do we compare one system with another, right? I mean, do we like make polls and ask people which one do they like more, or do we come up with some more objective metrics, like in the case of computer vision? That's still an active research area. I like to think about it that it's still the humans who are being creative in the way that in the way they use the neural networks, but also certain generative musical neural networks seem to have like a flavor of their own. So like GANs are kind of more chaotic than, let's say, a transformer. So I wouldn't call them creative, at least yet, but I'm interested in what comes next.
Are there AI tools to identify plagiarism? This topic I know.
Yes, there are. There are models that can disambiguate cover songs, and this is also a active research area. I think that even last ISMIR, there's been some paper about it, and I think that the upcoming ISMIR, there's also something about cover song detection. When you have all these capabilities of analyzing music with deep learning and other algorithms, you can just start looking for patterns or melodies that are similar. But this is also like a complex case also from the legal side, because there's people suing other people over copyrights, and some people win and some people lose, and it's still, you may have heard about the Dark Horse thing with Katy Perry. So that was like an ongoing thing where people were accused of plagiarism, etc., etc. But yeah, there's definitely AI methods that can compare and look for similarity in audio.
And a humorous one, is AI gonna replace audience also?
I hope not.
Okay, next one. Do you think AI will kill all of us, or at least will replace us on music creation generation?
Well, I hope it doesn't kill all of us. You know, there's a social event tonight, so we can expand on this topic maybe later. But I'm all for co-creation of music between humans and AIs.
And the last question from Julf. Is MIDI still used today? What for?
It's still used for producing like 80% of the music that you're hearing, because only in very specific cases you make recordings of only live instruments. Because I mean, for example, in classical music or like in acoustic jazz, etc., like probably you wouldn't use these type of instruments, but like almost anything else and music that's produced and mixed in like real world actual production environments, most is produced using MIDI, because it just gives you the flexibility. You can just play the part and then change the sound afterwards. Like when you record a grand piano, you can't change that into like, let's say, an electric piano, like in post-processing. That's like impossible. With MIDI, you can turn it into anything that you want. So MIDI is like totally still used all the time in actual music production and performance, like all the time.
So it looks like those are all the questions. So Mateusz, thank you very much for giving us this great talk.
Thank you. Thank you. I enjoyed it a lot. Thanks.